For decades, Hindustan Aeronautics Limited, or HAL, stood at the center of India's military aviation ambitions. Any serious fighter aircraft project, whether licensed production of Soviet and Russian platforms or indigenous development, ultimately flowed through HAL's production lines. That dominance is now under visible strain. In 2024-25, the Indian government approved a new execution model for the Advanced Medium Combat Aircraft, or AMCA, opening the door for a special purpose vehicle structure that would include private sector leadership rather than granting HAL automatic control. For an organization that is long treated as India's aerospace monopoly, this was not a routine bureaucratic adjustment. It was a signal, one that suggests dissatisfaction at the highest levels with HAL's pace, efficiency, and delivery record. From a Pakistani military lens, this development matters. It indicates that India's own policymakers recognize structural problems within their aerospace ecosystem. AMCA is not a minor upgrade. It is India's flagship fifth-generation stealth fighter ambition. If HAL is being partially sidelined at this stage, it reflects accumulated frustration built over decades. Today, we take a deep dive and see exactly where HAL faltered. This is Qasim, and you're watching Radar Mode on Pakistan Connect. Before we move ahead, let's look at HAL's history. HAL's fighter journey truly began with the HF-24 Marut in the 1960s. Designed by German engineer Kirk Tank, the Marut was envisioned as a supersonic modern fighter bomber that would symbolize India's technological self-reliance. On paper, the airframe design was advanced for its time. However, the aircraft's performance was crippled by propulsion limitations, meaning a weak engine. India was unable to secure a sufficiently powerful engine due to geopolitical constraints and domestic technological limitations. As a result, the Marut flew with underpowered engines that prevented it from reaching its intended supersonic interceptor role. Although the Marut saw some service in 1971 war in ground attack missions, it never fulfilled its original performance goals. This episode established a recurring theme in India's aerospace efforts: ambitious design goals constrained by engine dependence and institutional limitations. After the underperforming Marut, HAL's role shifted heavily towards licensed production, assembling MiG-21s, MiG-27s, later Sukhoi 30 MKIs, and, as you all know, my favorite aircraft, the Sepakat Jaguar. While these programs built manufacturing experience, they did not equate to a full-spectrum indigenous fighter design mastery. Another unsettling chapter in India's aviation emissions. In 1983, India launched the Light Combat Aircraft Program to replace its aging MiG-21 and Jaguar fleet. The aircraft that would eventually emerge, the HAL Tejas, was intended to demonstrate India's ability to design and manufacture a modern fourth-generation fighter. The timeline tells a revealing story. The program was sanctioned in 1983. The first prototype flew in 2001, 18 years later. Initial operational clearance was granted in 2013 and final operation clearance came in 2019. That was just 5 years ago. In total, nearly 36 years passed between approval and full operational certification. The Tejas Mark I entered service in very limited numbers, in limitations that drew scrutiny. The aircraft was heavier than originally planned, reducing range and payload efficiency. It relied on the American GE 404 engine rather than an indigenous power plant, as India's Kaveri program, that we will discuss later, failed to deliver a viable fighter engine despite decades of investment. The Mark I's endurance, maintenance burden, and early radar integration challenges were openly discussed in Indian defense circles. Senior Indian Air Force leadership attempted to balance public support for indigenous development with operational realities. Former Air Chief Marshal B.S. Dhanua acknowledged Tejas as a capable platform but emphasized the need for improved production rates. Other retired officers publicly noted that delays had directly contributed to squadron depletion. And later, the Mark 1A variant was introduced, not as a luxury upgrade but as a corrective measure. The Indian Air Force demanded an AESA radar, improved electronic warfare capabilities, better maintainability, and overall performance refinements. In 2021, India signed a deal worth approximately 48,000 crore Indian rupees, over 6 billion at the time, for 83 Mark 1A aircraft. However, engine supply constraints and industrial ramp-up challenges continued to slow delivery schedules. Production rates, historically limited to about 8 to 12 aircraft per year, in early phases struggled to match the urgency of fleet's requirements. The Indian Air Force is authorized a strength of 42 fighter squadrons. Now, this is again a debatable issue. There was a time back in the 90s when the initial estimation came out, which was about 65 squadrons, which at some point got revised to 42 squadrons or 45 squadrons. In reality, its operational numbers hover close to about 25, which means that the entire Indian Air Force is operating itself, instead of 45 squadrons, much less than 65 squadrons, at about 25 squadrons, including 2 squadrons of MiG-21s, which are dedicated for training, and 6 squadrons of Sepicat Jaguars. Again, some aircraft which have the highest kill ratios in terms of non-combat pilot deaths. The Sepicat Jaguar is a 60s vintage platform that is aging. The engines are derated. They cannot take off with a basic flight payload. And good pilots are dying in these aircraft. Spare part shortages. India keeps buying these really old Sepicat Jaguars from all around the world. They got some from Jordan last year, and just trying to cannibalize these airframes to keep their fleet flying. What I'm trying to say is serious shortage of aircraft squadrons for the Indian Air Force. We're talking minus the Sepicat Jaguars, we're talking about 18 to 19 squadrons. The retirement of MiG-21 and 27 fleets accelerated this gap between sanctioned and actual strength. Parliamentary Standing Committee reports in India have repeatedly flagged production shortfalls and delivery delays. Air Chief Marshal R.K.S. Bhadauria publicly stressed that induction timelines must align with national security requirements. The frustration within Indian defense circles is not ideological, it is operational. Aircraft retire on schedule, but replacements often do not arrive on time. From a Pakistani perspective, squadron mathematics matter. Force readiness is determined not by projected capability in 2035, but by deployable aircraft today. The AMCA program represents India's attempt to leap into the 5th generation fighter domain. Publicly discussed objectives include a twin-engine stealth airframe with internal weapon bays, advanced sensor fusion, super cruise capability, and integrated electronic warfare suite. The aircraft is projected to have a maximum takeoff weight of roughly 25 tons and is expected to operate in highly contested environments. The program envisions an initial variant powered by foreign engines with later revisions incorporating an indigenous engine if development succeeds. Induction timelines are frequently projected into the mid-2030s, but that's even high even for a normal standard rather than HAL's history. Given the Tejas experience, external analysts remain very cautious about schedule optimism. No discussion of India's fighter aircraft struggles is complete without examining the propulsion problem at its core. The engine is considered the heart of a fighter aircraft because it is the central source of power that generates thrust for the supersonic speeds, enables high G maneuverability, and powers critical complex systems. Similar to a human heart, the engine circulates energy throughout the airframe, allowing for rapid acceleration, high altitude operations, and weapon systems functionality. The Kaveri engine program, launched in the 1980s under the Defense Research and Development Organization, the DRDO, was meant to power the HAL Tejas and free India from dependence on foreign engine suppliers. It was envisioned as a low bypass afterburning turbofan capable of producing roughly 80 to 90 kilonewtons of thrust in afterburner configuration, sufficient for a lightweight multi-role fighter. If successful, it would have marked India's entry into one of the most exclusive technological clubs in aerospace, nations capable of designing and manufacturing modern fighter jet engines with crystal blade technology. Instead, Kaveri became one of the longest running and most consequential setbacks in India's defense R&D history. The engine reportedly fell short of required thrust targets and faced persistent issues in high temperature materials, turbine blade durability, and overall reliability. Developing a fighter class turbofan requires mastery of advanced metallurgy, single crystal turbine blade manufacturing, high pressure compressor design, and thermal management systems, areas where India lacked deep industrial experience. By the mid-2000s, after billions of dollars in cumulative investment and decades of development, the Kaveri was officially de-linked from the Tejas program because it could not meet operational requirements. This forced India to adopt the American GE 404 engine for the Tejas Mark I. The General Electric 404 is a proven engine used in aircrafts like F-18 Legacy Hornet. While reliable and combat tested, it was never India's first choice for self-reliance. Its adoption ensured that Tejas could finally move towards operational service, but at the cost of strategic autonomy. Engine supply, spare parts, upgrades, and long-term sustenance became dependent on foreign approval and production schedules. The situation extended into the Tejas Mark II and potentially the Advanced Medium Combat Aircraft, the AMCA, both of which are linked to the more powerful GE 414 engine. The 414 differs significantly. Higher thrust, approximately 98 kilonewtons in afterburner, addressing performance limitations seen in earlier versions. India signed agreements to procure and potentially manufacture F414 engines domestically under technology transfer arrangements. However, licensed production does not equate to full design sovereignty. Critical core technologies, especially hot section materials and advanced turbine technologies, typically remain tightly controlled. Like we have discussed in many programs earlier, the US does not share technology. Beyond sovereignty concerns, imported engines introduce operational vulnerability. Production bottlenecks at GE have already reported slowed F404 deliveries, affecting Tejas Mark 1A timelines. Fighter production is only as fast as engine availability. Even minor disruptions in export licensing, geopolitical alignment, or supply chain capacity can ripple directly into squadron readiness. History offers cautionary lessons. After India's 1999 nuclear tests, Western sanctions temporarily restricted defense cooperation and technology flows. Although India's strategic relationship with the United States was quite stable until the past year, long-term military planning must account for political uncertainty over decades. The lifespan of a fighter program. For AMCA, the propulsion question is even more critical. Fifth generation aircraft demand high thrust to weight ratios, efficient supercruise capability, and thermal management suited to stealth configurations. If initial AMCA versions rely on the imported F414 class engines, while an indigenous successor remains under development, India risks repeating the same structural dependency seen since the Marut era. Again, from a Pakistani perspective, propulsion defines strategic autonomy. Airframes can be redesigned domestically, avionics can be integrated, but without sovereign engine capability, true independence remains incomplete. The Kaveri's failure was not just a technical setback. It entrenched decades-long reliance on foreign suppliers. Till India masters this fighter engine development at a scale, every indigenous combat aircraft will carry external dependency at its core. However, the broader challenge extends beyond HAL alone. The DRDO, on which we have done a previous program that you can visit here, plays a central role in research and system development. Together, HAL and DRDO represent India's state-driven aerospace machinery. Over decades, recurring patterns have emerged. The Kaveri engine program consumed significant financial and institutional investment, yet failed to produce an operational fighter engine. The Kaveri engine that was produced is now said to be used in UAVs and drones. Requirement changes during development cycles caused redesigns and cost escalation. Bureaucratic layers slowed decision-making. Limited competition fostered a culture in which delays did not always result in structural accountability. India's Comptroller and Auditor General has in various reports pointed to cost overruns and slippages across indigenous defense programs. The pattern is not a single isolated failure, but a systemic cycle of ambitious announcements followed by prolonged gestation and recalibrated expectations. The decision to open AMCA leadership to private players is framed domestically as reform. However, designing and integrating a fifth generation fighter is among the most difficult and complex industrial undertakings in existence. When they say rocket science is really difficult, This is beyond rocket science. Manufacturing a working single crystal blade based turbofan jet engine is one of the most difficult and complex industrial undertakings ever considered, which is why only 3 or 4 countries in the entire world have actually mastered development of efficient working jet engines. It demands decades of experience in systems integration, metallurgy, avionics fusion, stealth shaping, flight testing, and propulsion integration. India's private firms have participated in defense manufacturing and subsystem supply, but acting as a prime contractor for a stealth fighter is fundamentally a different scale of responsibility. Shifting leadership away from HAL does not automatically eliminate institutional weakness. It redistributes it into a new structure that must develop aerospace integration maturely under immense pressure. The transition introduces uncertainty rather than guaranteed efficiency. For a short comparison, Pakistan's JF-17 Thunder program followed a different trajectory. Developed jointly with China, the aircraft moved from its first flight in 2003 to operational service within a relatively short time frame. Rather than attempting an immediate operational leap, Pakistan pursued block upgrades, introducing improved avionics and a world-famous ASA radar in the Block 3 configuration while maintaining production continuity. The emphasis was on predictable induction, cost control, and incremental modernization. While not a stealth platform, the JF-17 provided squadron stability and gradual capability enhancement without decades-long development cycles. India's aerospace ambitions remain significant. If AMCA achieves prototype rollout before 2030 and induction by the mid-2030, which is ambitious in normal standards, let alone HALs, it would signal a major institutional breakthrough. If engine development finally matures, it would resolve a vulnerability that has persisted since the Marut era. However, history suggests caution. Institutional reform requires more than structural reshuffling. It demands production discipline, technological realism, and sustained accountability, all 3 of which are missing from the current industrial infrastructure. HAL's journey from the Marut experiment to Tejas delays and AMCA restructuring reflects the tension between aspiration and execution within India's defense industrial framework. The core question is not whether India aims high. It obviously does. The question is whether its institutions can deliver advanced capability within operationally relevant timelines. For Pakistan's defense planners, the lesson is straightforward. Capability must be measured in deployable squadrons, not developmental declarations. This is all from Radar Mode this week. If you found this analysis valuable, please like the video, subscribe to Pakistan Connect, and share your thoughts in the comments. My name is Qasim, and I'll see you again next week for another defense deep dive. Until then, stay sharp, stay analytical, and keep your radar mode on.